What we still need to formally define is when an action is applicable in a state and what the corresponding state transition is. To do this, I will first introduce a little notation. Suppose we are given a set L of literals, so these are positive and negative atoms. Then I can use this here, this symbol L+, to refer to those atoms that are positive in L. And I can use L- to refer to those atoms whose negations are in L. So L+ and L- are sets of atoms, namely those that are positive and negative in L respectively. Now, let A be an action and S be a state. And when I say action here, I mean action, a ground instance of an operator. Then we can say that the action A is applicable in the state S if two conditions hold, namely all the positive preconditions of A, preconditions plus, of A, must be a subset of the state S. And we also want none of the negative preconditions of A to be in S. And this can be expressed by this expression. The intersection of the negative preconditions and what is in the state S must be empty. In other words, there cannot be a negative precondition that is also true in the state. A is applicable in S if all the positive preconditions hold in S and none of the negative preconditions hold in S. And now we can define the state transition function gamma for a given state, that's the state in which we are initially, and the action A that we are applying in this state. And this can be defined as follows. We start off with a state and we deduct all the negative effects. As I told you earlier, this is the delete list, so we delete this from the state. And then we add all the positive effects, so we add them to the state. And again, I've already explained, this is the add list. So we start off with a set of ground atoms, we remove some ground atoms, and we add some ground atoms. And this is the state that we get as a result of applying the state transition function in state S using action A. One minor point that is of quite a lot of importance in some detail is that we first delete the negative effects and then add the positive effects. That means if there is an atom that is a negative effect and a positive effect, it will be in the resulting state because it is first removed and then added again. You may wonder, why would you ever want to have an action that has the same atom as a negative and positive effect? Well, maybe have a look at the move action that we've just introduced and see whether this would ever be possible that an atom can occur as a negative and a positive effect depending on what values I choose for the variables. Finding the actions that are applicable in a given state is actually a non-trivial problem. You can see this quite easily when you think about the number of possible actions that may be applicable in a given state, namely all those operator instances where you replace every parameter by every possible value. That would give you an exponential number of actions. In general, there are way fewer actions applicable in a state, though. And here is an algorithm that you can use to find the applicable instances of a given operator in a given state. This function addApplicables takes 5 parameters. The first is A, the set of actions, and this is initially empty. This is just the set in which we collect the result of this function, so the applicable actions. Then we give it an operator of which we seek instances that are applicable in our state. We have a set of remaining preconditions of this operator, so these are the preconditions we still need to look at. Initially, these are all the preconditions of the operator. Then we have a substitution for the variables that are parameters of the operator. Initially, no variables are replaced by values. And then, of course, we have the state in which we are trying to apply this operator. So the algorithm will first deal with all the positive preconditions. So it first tests whether there are positive preconditions left. And if there are none left, it goes to the first part here. And if there are positive preconditions left, it will go to the second part here, the second part of this if statement. And the first thing we do is select the next positive precondition that we are trying to apply to restrict the actions that we can apply in the state. So PP is the positive precondition that we look at next, and then we go through all the propositions in our state, here SP, and try to match this against PP. Of course, If the predicate doesn't match, it can never be a match, and therefore we can ignore these. We only need to look at those propositions that have the same predicate. And then we extend the current substitution that we were given as our parameter such that the two SP and PP match. This gives us a new substitution. And if this substitution is valid, it means we were able to extend the substitution. Then we can do a recursive call. And the recursive call goes as follows. We don't change the set of actions in this case. We simply use the same operator again. We remove the precondition from the set of preconditions that we've just dealt with. So PP is the one we've just exploited. We no longer need to look at that. We've changed the substitution by adding more values to variables, and the state remains the same. We go through this loop until there are no more positive preconditions, and then we end up in the first case of the if statement. So now we've dealt with all the positive preconditions. We now look at all the negative preconditions. So we loop over NP, where NP is a negative precondition. And all we have to do is now check whether our state falsifies this negative precondition. If this is the case, then this cannot result in an applicable action. But if the state does not falsify the negative preconditions, then we have found an instance of this operator op that we were given that is an applicable action in this state. And that what we have to do is simply replace all the parameters of this operator according to the substitution that we've been building up. Here's an example that should illustrate this algorithm. In this example, we are given our state over here. That's the set of ground atoms, and we have our PDDL action defined here. That is the move action we've seen previously. So these are the two parameters we've seen in our algorithm. That's the operator is the move action, and S is the state we were just given. The other parameters are an empty set, the preconditions of the move operator, and an empty substitution. The algorithm then starts by testing whether there are positive preconditions left, which is the case, which means we immediately go to the else part of the algorithm. And the first thing there is we choose the next positive precondition we want to look at. So let's go back to the example. The first positive precondition is adjacent from 2, and this is the first precondition we will pick here, so that's PP. PP is this adjacency relation. Looking back at the algorithm, we see that the next step is to look for all those state propositions that can match this positive precondition. So let's look at our state. This is the adjacency relation, and we have two adjacency ground atoms in our state, namely location 1 to location 2 and location 2 to location 1. So these are the two cases here I've listed for SP. The loop will go through those two and succeed there. The next step in the algorithm then is to extend the substitution such that SP and PP match, and we can see this has happened here. I'll go through the first case on the left here. We've extended the substitution such that the variable from our precondition must be location 1 and 2 must be location 2. So that adjacent log1, log2 matches what we have here in our substitution. The algorithm then continues with the recursive call because the substitution is still valid, and it simply removes that positive precondition from the preconditions that we still need to do. So again, we end up at the entry to the algorithm, see that there are positive preconditions left, end up in the else branch, and select the next positive precondition that we need to deal with in the algorithm. And as we can see here, the next positive precondition is at R from. So that's the next positive precondition we select. And we need to match that against the state. Let's look at the algorithm again. So we're now here that we're going through a loop over all the propositions in the state that match this positive precondition. And if we look at the at relation in the state, there is only one option here. So this loop is only one long. And we choose this here. So we try to extend the substitution such that it matches this state proposition. And what we see here is that we need to match R to R1 and from to location 2, but in our substitution previously we've already said that from must be location 1, so it can't be location 1 and location 2 at the same time, which means our substitution is not valid. But if we go back to the algorithm, we had a branch here previously in this loop that we haven't explored yet, and that is listed here, namely where SP was adjacent location 1 to location 2. And again, what we do is extend our substitution such that the state proposition matches the positive precondition. And we can do that here. So we have that our new substitution maps from to location 2 and 2 to location 1. Again, this is followed by the recursive call, so we need to check whether there are more positive preconditions, just like in the other case. And yes, there is another positive precondition, the same one we dealt with in the other case, the at relation. And again, there is only one possible instance in the state that can match that, and that's at R1 location 2. So where are we now in our algorithm? We are here. We need to extend the substitution such that the state proposition matches the positive precondition. So let's go back to the example. What we have here is we need to match R to R1, and again we can do that. We match from to location 2, and again previously we had matched from to location 2, so this is consistent with the way we need to match from now, which means we can actually in this case extend the substitution and have a new substitution, in which case from is location 2, 2 is location 1, and R is R1. So again, this would be followed by the recursive call here, and that means we reach the algorithm with a set of empty positive preconditions. There are only negative preconditions left. Let's look at the example. We've dealt with adjacent and we've dealt with at. So there are only negative preconditions we need to deal with. And the negative preconditions, then, that's this part here of the algorithm. We go through every negative precondition and check whether this is falsified in the state, instantiated with our substitution sigma. So what does this look like in the example? So there's only one negative precondition in our example, namely that we want the location we're moving to not to be occupied. And that is our NP now, which means it is not occupied location 1. In the example, the variable we're instantiating is 2, and our substitution tells us that 2 must be location 1. So this is the instantiated negative precondition, not occupied location 1. And as we can see in the state, the only location that is occupied is location 2, which means our negative precondition is not falsified here. So we can turn this into an action that we add to the set A. That's the final step here. So we add to A the instance of this operator instantiated using our substitution that we've defined here. That was the last substitution we had. And we get the operator move R1 from location 2 to location 1. And indeed, this is the only applicable action here, and that means we are done with this algorithm.